Well, hi there, sports fans, and welcome to another exciting edition of Physics 12. And today we're looking at lesson 3.3, which is on the work-energy theorem. So energy was traditionally defined as the ability to do work, and we know that there actually are some forces that are not able to do work. However, this shows up in more advanced physics. The type of things that we're going to be looking at with mechanical energy, it does follow this definition. So for our intents and purposes, energy is defined as the ability to do work. Now, sometimes when we do work, we make objects move if they're at rest. If they're moving, then they will speed up or slow down, depending on what the case may be. So we can add energy to a system or takes energy away from a system. So if you look at an example of this, here's a bus that's moving down the road at a certain velocity, and there's a net force that's applied to the bus. And so after a certain distance, it now has a different velocity, which is greater than the first velocity or the initial velocity. So here this is labeled V2, but this would be considered V final, and this would be V initial. All right, well, we know that the work done on the object is the force times the distance that it's applied for. And we also know that force equals ma on an object, and so we can substitute that in for force, which means then that the work done on an object will equal its mass times acceleration times the distance that the acceleration acts on the object. And now I'm just going to pull a rabbit out of a hat here, and I'm sure that this won't be a problem for you, that 1/2 times 2 does equal 1. And when you multiply anything by 1, you don't change its value at all. So we're going to make use of this and put those numbers in here as well. So the work equals 1/2 times the mass times 2AD. Now we have 1/2 times 2, which is just 1, so it doesn't change the value of it. It just allows us to see something that we recognize, which is 2AD, which is part of an equation that we worked with before. And we know that V final squared equals V initial squared plus 2AD. So we can change that equation around. 2AD equals V final squared minus V initial squared. And we can substitute that into this equation here. And so then what we end up with is work equals 1/2 times the mass times V final squared minus V initial squared. And so what that means is that if we write the acceleration in terms of the velocity and the distance, we find the work done here is, the net work is 1/2 mv final squared minus 1/2 v initial squared. And we define the kinetic energy as 1/2 mv squared. And that is the definition of kinetic energy. So what that means then is the work done is equal to the change in the kinetic energy of an object. So if you do work on an object, you will change its kinetic energy. So the net work has to equal the change in kinetic energy. As we said, you can add energy or take energy away from a system depending on if it's positive or negative work. So if the net work is positive, the kinetic energy increases, and if the net work is negative, then obviously the kinetic energy will decrease. So that's the first type of energy we're going to look at least for mechanical energy. And the other type we'll look at is what's known as potential energy. So an object can have potential energy by virtue of its surroundings. And some familiar examples of potential energy are a wound-up spring. So if you compress a spring, then that spring will possess some potential energy. Also, if you stretch an elastic band, by stretching it, you introduce some potential energy to the elastic band. And also, an object that's raised to some height above the ground also will obtain potential energy by that lifting. And so let's see how that works then. So here we have an object that's on the ground, and it's being lifted by some force to a distance above the ground. And so in raising the mass to the height h, the work done by the external force is, work will equal the force times the distance it's applied for. So that distance will be from the starting point to the end point up here. And the force needed to do that is just going to be the gravitational force of the object. So that just equals mg. And if the distance, we call that h, then the work done in this object will be mg times h. And we therefore define the gravitational potential energy as mgh. So potential energy is mgh, and this is the other type of mechanical energy that we are looking at. So this potential energy, it can become kinetic energy then obviously, if the object is dropped. So you can go back and forth between forms of mechanical energy. So kinetic energy can become potential energy, and potential energy can become kinetic energy. Now, we have to differentiate as well between conservative and non-conservative forces. So, for example, if you have friction that's involved in the movement of an object, that would be an example of a non-conserving force. So that has to be accounted separately in terms of our work energy equation, which we will look at in just a minute. So if friction is present, the work done depends not only on the starting and ending points, but also on the path taken. So friction is what's referred to as a non-conservative force. So there are other types of non-conservative forces. First of all, the conservative forces are gravitational, elastic, and electric. With the first part of the course, this being the looking at mechanics, we're looking mostly at gravitational forces, and that's being accounted for with potential energy. Later in the course, we will look at electrical forces. Elastic we don't deal with too much because that has to do with changing forces. So right now we will be concerned mostly with gravitational conservative forces, or the gravitational force, which is a conservative force. And all of these other ones are non-conservative forces, and they can either take energy out of a system or they can add energy to the system. And so they need to be dealt with separately. And so potential energy can only be defined for conservative forces. So if we have non-conservative forces, then we have to account for them differently. And we distinguish between the work done by conservative forces and the work done by non-conservative forces. So we find that the work done by non-conservative forces is equal to the total change in kinetic and potential energies. And so our equation then looks like this. If we have a non-conserving force, like the list that we just looked at, the work done by that force will have to equal a change in kinetic or potential energy, or both. And so that's going to be reflected by that equation there. So a non-conserving force is part of our equation here. And then the two other mechanical forces that we look at are kinetic energy, the two other mechanical energies that we look at are kinetic energy and potential energy. And so we will be looking further into work, and we will be using the work energy equation, and we will see how potential energy can become kinetic energy and vice versa with some of the problems that we will be dealing with in this topic.